everyone, my name is Antonio Nathaniel, and today in this video we are going to be doing another episode in our mathematics for senior secondary school 2. And in this particular episode we are going to be dealing with vectors, and these vectors we are going to be dealing with it as the first class in vectors for mathematics. So wherever you are, just pay attention so that we can go on with this class. Now we are going to be talking about various concepts surrounding vectors. But if this is your first time of hearing about vectors, vectors is simply a quantity that has a magnitude and direction. Now up till now we've been dealing with algebraic processes, symbols, variables and all the rest, and those have been scalars, right? They have only magnitude, they don't have direction. But when we talk about vectors, a vector is something that has magnitude and direction. What I mean is, when you have something that has magnitude and direction, it means that thing can both increase and decrease, and then it can have both the positive and the negative direction. For example, your forces, there's a pulling force and there's a pushing force, right? Now that pulling force could be the positive direction, and then your pulling force could be the negative direction. So that's just an example of how vectors work. It's not very difficult, but just for you to wrap your head around the fundamentals. So let's talk about the terminologies and the things to understand when speaking about vectors. Now, you will need to understand that a vector is a quantity that has both magnitude and direction. A scalar is a quantity that has only magnitude. So that's the difference. A vector has both magnitude and direction, but a scalar has only magnitude. The next, so another thing that we have to understand is that we can write vectors in a variety of ways. We can write vectors as in terms of, we can write them just like this. We can write the vector PQ as this, PQ with an arrowhead on top. So this is the general notation for a vector. It's acceptable, or you can just write it as P, vector P in capital letters, small letter P. You can just write it as P in bold and font. Just bold it. When you write P in bold and you in lowercase, it's also another notation for vectors. So either of this is it's acceptable, but most of the time you often see vectors with as a capital letters with an arrow on top, or you can see them as lowercase letters with bold face. They have been bolded. Now that being said, we also have vectors can also be represented as the Cartesian components of a point. Now the for example, if we're talking about if this is the origin, then we'll have a vector, and then this vector, this is the vector. Now this vector is represented by a line OP. Now this vector also points outward away from the origin. Now this particular vector we're talking about here, it has its own coordinate. This P has a coordinate x, y. Now if we were to represent this vector P as a in Cartesian coordinates, we'll say P, vector P in capital in bold, P in bold equals, or you can also say PQ with an arrowhead on top. That's the notation for vectors, equals the column vector x, y. So this is another notation for vectors. You can represent them as column vectors. This is also acceptable. That is when you have represented your vectors on the Cartesian coordinate. So this is the OP. This vector OP, let's call it OP rather. This is OP, not PQ. OP. Vector OP is represented as the column vector in terms of its Cartesian coordinates. Now that's how we do vectors. Now you can also add vectors, you can subtract vectors. We are going to get there. Now parallel vectors are vectors that have the same direction, and equal vectors have the same size and direction. Now there's a difference between these two. Now parallel vectors, they have only their directions equal. For example, if I draw a line parallel to this line OP, if I draw another line x, y, if I draw another line q, r parallel to this line OP, now these two vectors will be said to be parallel. So they are parallel vectors because they are in the same direction only. But if two vectors have both the same magnitude and direction, that means if this QR is also as large as OP in terms of magnitude, and we'll also be talking about the magnitude of the vector soon. But if this QR has the same magnitude as OP, then it is said to be an equal vector. It will have the same size and direction. Next, we also have equivalence vectors. Equivalence vectors, they are even more closer than equal vectors, because equivalent vectors, they have the same points of application, they have the same size, and they have the same magnitude. So these are just the terminologies that are associated with vectors. So you can just begin to note them down, or you can just listen carefully so that you can be able to understand them. So that by the time we begin to talk about the questions and calculations, you won't have issues with any of those. Now, the modulus of a vector. Yes, the modulus of a vector is a positive scalar quantity that represents the magnitude of the vector. Now, the modulus of a vector gives us its magnitude. The modulus of a vector is also known as the magnitude of a vector. So now, if we are representing this column vector now, this column vector xy, when we are looking for the modulus of the vector, we'll denote it as the modulus of the vector PQ, of the vector OP is denoted as OP with vertical slashes, the vertical slashes on it. Then OP, the magnitude of the vector, will be equal to the square root of the square of the x and the y coordinate, coordinate. That's root x squared plus y squared. So that would be the distance x and y. That would be the square root. So, but at the beginning we are dealing with two different coordinates. Now, if the initial position of the vector is x1, y1, and then the final position of the vector is x2, y2. Then we also have so if this is the notation, then vector QR will be denoted as x2 minus y2. This is the modulus of the vector QR plus x2 minus x1 plus y2 minus y1 square. Now, this is x2 minus x1 square plus y2 minus y1 square. So this is how to represent the modulus of a vector. So if it involves if it has been represented on Cartesian coordinates, that is the modulus of a vector. Now moving on, and if it was a column vector, the modulus of a vector is simply root x square plus y square. So, but if it is in form of a the distance between 2 points, so the modulus of a vector of a vector that is represented by a line is simply the distance between, or the length of that line. The modulus of a vector that is represented by a line is simply the length of that line, and the length of a line in Cartesian coordinates is simply this formula: root x square x minus x1 square plus y2 minus y1 square. Now moving on to the next terminologies, we have the zero or null vector has a zero magnitude. It has no magnitude and no direction, and it is written as 0 or a column vector 0. Now it is written as 0, column vector 0 and 0. So this is a vector that has no magnitude. It is called a zero vector or a null vector. Now, if you remember in our SS1 course, we talk about sets, right? Now, in those sets, we also have what is known as your zero or null set. Now, your null set is just analogous to your zero or null vector. So, but they are not the same thing. I'm just using this as an analogy to compare and make you understand better. Now, the next terminology: if vector A is multiplied by scalar k, then the product is vector Ka. So, and it's a vector that is k times the size of A, vector A, and in the same direction. And vector minus A is the same size of A, but in the opposite direction. So what we are doing now, we are doing a manipulation on the vector A. Imagine we have the vector A. This is bold, A in bold. Now, if we multiply this A by a scalar k, that means this will be A times k. K is a scalar. Then we will get a new vector Ka. Ka in bold. Now, this is an operation on vectors. Then also, if you have a negative vector A, it is the vector that is in the opposite direction of vector A. So negative A is also a vector, but it's in the opposite direction of vector A. So this, if we say negative P, will be the vector that has the same size as P, but has an opposite direction as P. So that is how we denote those. And next, let's move on to vectors PQ and QR can be added using the law of addition. Now, whenever you want to add vectors as column vectors, when you want to add them, you just if you have the first vector as A, B, and the second vector is C and D as column vectors, then you just add them. So that means your result will be what? You add the top that's A plus C, then you add the bottom B plus D. That would be your new result. For example, if you have a vector 2 and 3 column vector, then you also have another one 2 and minus 3. Now if we were to add these two vectors, we'll just add them together like this. That's 2, 3 plus 2 minus 3. Now the 2 plus 2 is 4. 3 plus minus 3, that's 3 minus 3, that's 0. So our new vector will be 4, 0. 4 and 0, the column vector 4, 0. So that is the new vector. And it also works for subtraction. If it's for subtraction, you just subtract the second from the first, and it works in the same way. So that is vector addition. So now let's move on to yeah, that's vectors. We've talked about vector addition and vector subtraction, just the change of sign, but still the same method. Now next, let's talk about what a unit vector is. A unit vector is a vector that has a magnitude of 1. So it is represented by a column vector 1 and 0, 1 and 0, or 0 and 1. It is a vector that has a magnitude of 1 only. Now, they are called base vectors. A unit vector is also known as a base vectors, and is written as I and J. Now, this is where we get to Cartesian in proper. We deal with Cartesian coordinates and vectors in proper. Now, when we are dealing with unit vectors, we have the unit vector in the x direction is denoted as 1, 0, and the unit vector in the y direction is denoted as 0, 1. Now, these are also known as the unit vector I and unit vector j. So that is what they mean. So if you have to represent this on the Cartesian coordinates, so this 1, 0 will be the x1 and y0, that's on the x-axis. That's this vector that is a one unit in the x direction. We can call it vector ox. So that would be vector I. That would be, and then if we're representing this 0, 1 column vector, that would be 0 and 1. That is one unit in the y direction, and to be j. Let's call it oy, vector oy. So vector ox is equals to I, vector oy is equals to j. Now, for any vector that has both x and y components, you only be expressing it in terms of both I and j. So for example, if you have a column vector 2 and 3, now and you have to represent that in terms of the unit vectors I and j. So this will simply equals to 2 this is equals to 2 times 2i plus 3 times j, because I and j, they are unit vectors, because that's the same thing as 2 times 1, which is 2, and this is the same thing as 3 times 1, which is still 3. So this column vector is represented as 2i plus 3j. So that is how to represent a vector in terms of the unit vector I and j. So most of the time in your questions in vectors, you'll be dealing with those, and even when dealing with transformations, we'll also talk about those. I'll give an example on that too. So now, having talked about this so far, let's talk about the angle that a vector. Okay, yes, let's talk about the angle that a vector makes with the x-axis. So first of all, let's talk about the components of a vector. Now, these are the components of a vector. This is the x component of a vector, and this is the y component of a vector. Now, let's talk about the angle that a vector makes with the x-axis. Now, the angle that a vector ai plus bj makes to the x-axis is equals to theta equals tan inverse of b over a. That's how it is. So for this one, if we replace a and b by 2 and 3, that would be, for this particular vector, we have the angle it makes to the x-axis will be tan inverse of what's b is now 3 over what's a, that's 2. That's tan inverse of 3 over 2. That would be the answer. So you just evaluate that and you get the angle that a vector makes with the x-axis. So it's often required, and it's also known as the argument of a vector. Now let's talk about let me give a simple example of adding vectors. Now if I were to add vectors together and to get their final answer, I would just, for example, if this is vector AB with an arrowhead, we always represent them as this vector AB, and vector if this is vector okay, yeah, and if this is vector BC. Now if you were to add these two vectors, you just bring this AB, you bring the tail of one to the head of the other. For example, you bring this one to the head of the other, so you draw them. That's if you were to add vectors in geometrical methods. So you don't often, it's not even common to ask this kind of questions, but just in case, now you just move the vector, just draw a line which is parallel to this vector. So I'll just draw a line parallel to this vector. Then I will measure the length of this line, and you remember I said the length of this line will be the magnitude of the vector, right? So the length of this line, I'll cut it on this axis. I'll thicken it, and that will be my new vector BC. So I'll transfer vector BC here. Now at the end of the day, I will join the tail of A to the head of C. So at the end of the day, this vector AC will be the addition of vector AB and vector BC. So this vector AC is equal to vector AB plus BC. That's how it works geometric in geometry. So now if for example, if parameter this AB is equal to A and BC is B in bold, now this vector AC will be what? A plus B. That would be the new vector. Now that's simply what it entails. When you are adding vectors together, just join the head of one with the tail of the other successively. Even if you are adding three, the head of one to the tail of the second, the head of the second to the tail of the third, and so on and so forth. So you, at the end of the day, you join your final position with your initial position. For example, if I have vector, if I'm adding three vectors, this vector, this and this and this, and this is A, this is B, and this is C. Now what I'll do is I'll join the initial position with the final position with an arrow, with my arrows here. That would be this, and from here this new vector will be A plus B plus C. So this is just simply how operations of vectors occur. Now next, let's talk about one part of vector that I think you need to know, and that is when dealing with the transformation. So this is a part. I promise that in this transformation we are going to be dealing with them squarely in my subsequent videos. I'll be dealing in further mathematics, but because this is a mathematics class, this is simply mathematics, and you will not often need to be asked questions in vectors. So I will just keep it simple, and we'll stop at transformations in the basics. But then in the further mathematics class, which I will be making in videos, we'll also go further than this. So let's talk about transformations. We've talked about magnitude of vectors as the length of a vector line. We've talked about the direction of vector as the arrow is represented by an arrow. And we've talked about vector addition. We've talked about vector subtraction. So now let's talk about what if we are asked to transform a vector from one part of the Cartesian axis to another. So if we're asked to transform a vector from one part of the Cartesian axis to another, the simplest thing to do is just to add that transformation vector. So let me demonstrate that. So now in this example, we have a square OABC has coordinates. O as 0, 0, O is 0, 0, A is 3, 0, B is 3, 3, C is 0, 3. Now it is translated by a position vector OP with an arrow. So this is, you see, I tell you that this is the notation for a vector OP, because this is translation vector, and it is translated to square PQRS. Find the coordinate of PQRS if OP is translated to this, and then if OP, the vector OP is equivalent to 2 and minus 4. So now this vector OP has been represented as a column vector now. So all we need to do is, we are given the 4 vertices of a square, yes, or the coordinates of a square, and this time around we are asked to transform the square into another square PQRS using this same method. So now we sketch a coordinate. So if I was sketching the coordinate axis, this would be let's call this 1, 2, 3, minus 1, minus 2, minus 3. Let this be 2, 4, 6, minus 2, minus 4, minus 6, negative axis. Then positive y-axis, that would be plus 2, 4, and 6. Let's stop here. Now let's draw this square. Let's just sketch this square. Now the point O will be 0, 0 with this point O. Now point A is 3, 0. That's 3, 0. 3 on the x-axis and 0 on the y-axis. That's on the x-axis at the end of the day. Now 3, 3. 3 on the x and 3 on the y. So 3 on the x and 3 on the y. That would be this. Then we have 0, 3. That's 0 on the x and 3 on the y. So if we join these 4 points together, we'll get a square. So it is this square that we're asked to transform. So now we are transforming this square into another square, but now we are making use of a transformation matrix. So whenever you make use of a transformation matrix, you are going to perform an operation on that on this original 4 points using the transformation matrix. So because this transformation matrix, it's an addition, so we are just going to add these coordinates together. We are going to add the coordinates and we are going to get the final answer. So in this case, what we are going to do here is we are going to move each of these points by the magnitude of this transformation vector. So what I mean is the transformation vector, it has its x and y components. So we are going to be moving each of these points by the magnitude of those components. For example, let's start from O. The O is simply represented as 0, 0. And so when we transform this O, let's transform it into a column vector. That will be 0, 0 column vector. Then 3 and 0 will be 3, 0 column vector. 3 and 3 will be 3, 3 column vector. Then 0 and 3 will be 0, 3 column vector. Now a column vector is simply the vector that is it's in terms of column. When you represent the two components as a column, it's called a column vector. But this is a row vector. When you represent the two components of a vector as a row, these are the x and y components as a row. But x and y as a column is called a column vector. And we'll mostly deal with column vectors in mathematics because they are easy to understand. Now what we'll do, let's transform 0, 0. You simply add the vector to the point. So let's add, for each of them, let's add the transformation vector. That's 2, 2 and minus 4. Let's add 2 and minus 4. Let's add 2 and minus 4. We're adding in each case. And then lastly, let's add 2 and minus 4. So in the first instance, when we add this, the x components will add together to give 2. So our new x coordinates will be 2. So and then our y coordinates will add to be minus 4. So 2 and minus 4. So that will be our first new point. So next, let's say this one. So we have 3 and 3. Our x will add to 5. So that was, let's extend the coordinate to 5. So 3 and 2, that's 5. So we have 5 and minus 4. 5 and minus 4. We have this here. The next we have the third. We have the x add up to 5 and minus 1. That will be 5 and minus 1. So we have it here. This will be minus 1 here. Then lastly we have the last one adds up to 2 and minus 1. That's 2 and minus 1. So if we join these 4 points together, we'll see that this is a transformation. So we've transformed the square from this square OABC. This is A is 3, 0. OA, B is 3. So we've transformed it to P vector P Q. Yes, the Q is now 5, minus 4. PQ RS. That would be P. Yes, PQ RS. So that's simply how to transform a vector. So, but this is just one out of many applications of vector algebra and vector addition. You can apply them in various different ways, but this is the limit we'll be going in this episode. So if you want to know more, I will still be making up more episodes on vectors. But thank you for watching and see you next episode.